Assalamualaikum. Let's see lecture number 35. We will discussing deflection of the beam. Previously lecture, we will discuss um, uh, deformation under transverse load using equation of elastic curve through differential equation. Then previous lecture, we will discuss statically indeterminate beam using this equation of elastic curve. Now, there is another method using method of superposition, and with that you can solve statically determinate beams as well as statically indeterminate beams. So this method of superposition is supported by the value or equation of elastic curve and also and slope for the known problems. We will see uh, like for example, what is method of superposition? For example, if you have this beam, simply supported beam AB with a distributed load and with a concentrated load at D. So this I can divide into two parts. So first, I'm considering I will remove the distributed load of 20 kilonewton per meter, and I will only consider point load. So what will be the deflection at D? If I'm interested, what is the deflection at D? And the second part, I will find deflection at D, but considering only the distributed load, not the combined point load. By adding that, I can find deflection at D. Okay, and also deflection at maximum deflection and slope at different location. So this method of superposition is basically deformation of beam subjected to combination of loading may be obtained as a linear combination of deformation from individual load. Now this again the condition is same as we discussed in chapter 2, 3 when we talk about method of superposition for the statically indeterminate problem as well, that the stresses are within elastic limit and elastic proportional limit, and the deformation are very small, and we also apply the centimeter principle. Now this method of superposition is can be facilitated through table. That table contains solution for common types of loads and support. So that table, that is Annexure D of your book. So beams, deflection, slope. So this table is giving for the most of the known problems, and by combining those problems, we can find or calculate the deflection of the beam. For example, the cantilever beam with a point load at the end, y max will be at free end. So maximum deflection, slope, and this is equation of the elastic curve. So if you look at cantilever with distributed load, so this will give me the maximum deflection, this is slope at the end, and this is equation of the elastic curve. So if you want to slope, so if I derivate it with respect to x, so differentiate it with respect to x, so by differentiating it with respect to x, I will get the equation for the slope. Similarly, cantilever beam with the moment at the end. Now moment direction, if we change, so this sign will change. Similarly, if load sign is changed, that the maximum deflection and slope and sign will also change. Simply supported beam with a load at the center, and this is again simply supported beam, but A is greater than B, right? So this equation, and simply supported beam with a distributed load. These are showing the, this is from your reference book, Hibbeler, Mechanics of Material by R.C. Hibbeler. So delta is deflection, M is moment, deflection, moment, theta is slope, deflection, free end, shear force will be 0, bending moment will be 0, at pin, internal pin or moment will be 0. So these are showing, this is showing different boundary condition, and load condition on different type of support and beam. Okay, now how to use this table? Let's see a sample problem. Sample problem 9.7. For the beam and loading shown, determine the slope and deflection at point B. So we are interested what will be the slope and deflection at point B using those tables. Okay, so this can be divided into two loading. Now, if you look this, so if you consider the whole distributed load, like loading 1 minus distributed load from A to L by 2, so if we add both of them, so it will give me this original scenario. Now, for deflection YB, that will be equal to YB1, that is due to loading 1, and YB2, that is due to loading number 2. And similarly, theta B1 plus theta B2 will be equal to theta B. Means if I want to write the equation for deflection, so YB will be simply equal to YB1 plus YB due to loading number 2. Similarly, for the theta B will be equal to theta B due to loading number 1 plus theta B due to loading number 2, and we will find these values from the given table and in a given NXD. Okay, now if you look at NXD, this I'm showing over here. So if we consider loading 1, so with the loading 1 we know the deflection of the beam and slope of the beam. So this deflection will be minus WL4 by 8 EI, and the slope is minus WL cube divided by 6 EI. Okay, now for the loading 2, now this is you have to look carefully in this case. For example, now if you look at this from A to C, so let me change the color of my pointer so for more clarification. From A to C, it will bend as a curve because the loading is there. If you remember that the equation for curvature 1 over rho is facilitated by mx by EI, right? Now, from C to B, there is no movement, right? From C to B, there will be no movement. Now, what is it showing us? It's simply showing us that it will be constant slope from C to B, so slope will not change, and also because it will be a straight line. So if we can find the value of slope at C, it will be same at B. So that's why it's written over here. Theta B2 will be equal to theta C2. And what will be the value? So it will be simply, if you put L by 2 over here, L by 2 over here, so that will give me the slope, equation of the slope. So this will give me equation of the slope. If I put L by 2, and this will give me this slope value. Because this is for the whole length beam L, we are interested only L by 2. So that will become minus W L by 2 cube. So that will become L cube by 8. 8 multiplied by 6, 48. So EI. Now, the deflection. Now for the deflection, we can find till C by putting in this equation. So let me change the color again. So in this equation, if you put x is equal to L by 2, so this will give me yc2. So this will give me yc2. Now I know this deflection right from this yc2, but I want to find what is yb2. So yb2 is simply yc2 plus this distance. So how to find this distance? I know this angle theta, right? And I know this length L by 2. So I know the angle theta and I know this L by 2. So this will be what? So this length will be simply sine theta, right? Sorry, tan theta, perpendicular base. So if I want to write tan theta, that will be equal to perpendicular bound base, and perpendicular we have to find, that is equal to y, let me put yb prime and tan theta. And since theta is very small, so we can take tan theta is equal to theta. We know this value, that is L by 2. So what we have? Theta, this is theta, multiplied by L by 2 plus the deflection we already know by putting x is equal to L by 2. So this will give me the deflection at B. So that is 7WL4 divided by 384 EI. Okay. Now this will give you deflection at B and slope at B using for this relationship. Okay. Now combining the two, theta b1 we already calculated, theta b2 we calculate. So by combining these two, so this will give us slope at B, and similarly yb is equal to yb1 plus yb2 due to loading 1, loading 2, and this will give us the value yb is equal to 41WL4 divided by 384 EI. Okay. Now you can find these values using the equation of elastic curve as well, using this differential equation first. You can also use this differential equation as first. Okay. And with that you can find an equation of elastic curve and you can solve as well. But you can also solve using the those value for the known curve by doing the method of superposition. Okay. Now let's see, method of superposition can also implement on statically indeterminate beam. For example, if you remember this problem, we have a cantilever beam with a distributed load and we have a pin at point B. We already solved this problem in previous lecture. Okay, that was our concept problem number 9.2. Concept application, sorry, 9.5. Okay, we can apply method of superposition may be applied to can be applied to the static indeterminate beam. What we will do first, we will solve it by removing this RB, as we take as a redundant load. We remove it and we will find the deflection due to this P. Okay, then we will find deflection due to this redundant load YB. Okay, so using this we will get RB due to load, and we can find the reaction, unknown reaction, by using compatibility equation, because YB will be equal to YBW plus YBL, and this must be equal to 0. So designate one of reaction as redundant and eliminate or modify the support. Then determine the beam deflection without redundant support, and using this compatibility, read redundant reaction as unknown load, which together with the other loads must produce deformation compatible with the original support. And this will give us another equation, and with that we can find we can solve the statically indeterminate problem as well. So again, let's see a problem. This is sample problem 9.8. That is using the method of superposition to find a reaction uh, and also we have to find support at end A, slope at end A. What is slope at end A? So we have to find the reaction at A, B and C. So what is the reaction A, B and C, and what is the slope at A? Okay, because we cannot find reaction, it's a statically indeterminate beam, it's a continuous beam, so we have 3 reaction and 2 static equilibrium condition. So what we will do, we will take support at B as a redundant, and we will divide into 2 parts. So what we will do, we will see that what will be the deflection at B due to distributed load, and plus deflection at B due to that redundant load RB. And what will be condition we have? We will have that YB should be equal to 0, and that will be equal to YBW plus YBR. And we will solve it by looking at the table. Okay, so this is, and by using that we will able to get all the reaction, and we already know that if we take sum of forces is equal to 0 and sum of moment is equal to 0, so that will give us the 2 equation, and we have 3 unknown, so third equation we will get from this relationship, and we will solve it, we get the reaction. Since we know all the reaction, so we can easily find what is the slope at A. Now distributed load, deflection at B, so this is a simply supported beam with a distributed load. So this is the equation of elastic curve. So we have to find, if we put x is equal to L 2L by 3, the location at which we have a third support, so YBW will be equal to minus W by 24 EI 2 by 3 L4 minus 2L 2 by 3 L cube plus L cube into 2 by 3 L. So using this equation we put the value, so YBW is minus 0.01132 WL4 by EI. Now for the second one, for the redundant, so we have P. Now since for our case the P is acting upward, so we will take P negative in this equation, and we put again in this equation x is equal to, so is this equation x is equal to 2L by 3. So if we put x is equal to 2L by 3 and we solve it, so B, E and A is also given, so B is L by 3, and X is equal to 2L by 3. So when we put X is equal, and we put B is equal to L by 3 in this equation. So when we put the value, and P will be negative P. So because of the direction, so you have to remember, you have to be careful. So YR, that will become 3RB divided by 3EI 2 by 3L square into L by 3 to the square. So when you simplify it, so this will become 0.0164 RB L cube divided by EI. Now, what is the compatibility equation? So compatibility equation was YB, so that will be equal to 0 YBW due to distributed load plus YB due to concentrated load, that is RB. This must be equal to 0, means this plus this is equal to 0, and with that we get the value of RB. So if you equal to 0, so RB is 0.8688 WL. Now we know this reaction RB, sorry, and with that we can find the other reaction as well by taking sum of forces is equal to 0, sum of moment is equal to 0. With that we can calculate all the reactions of this continuous beam. Okay, now slope at A. Now slope at A, we have theta AW plus theta AR will be equal to theta A. So as shown over here. Now using this equation, so theta AW, so theta at A will be PB into L square minus B square divided by E 6 times EIL for the concentrated load. So that will become simply P will be replaced by a reaction at B, RB, that we calculated previously, and then we put the value in this equation. We know the B, we know EI in terms of EI, so that will become 0.03398 WL cubed by EI. Now, what is theta at A for W distributed load? So theta A at W distributed load, simply what you will do, if you differentiate it with respect to this will give you the theta W. Theta W on the free end, this point is showing theta W. So if you put the value, so maximum slope is at the end A C for the distributed load, so that will become WL cube divided by 24 EI minus, and simplifying, minus 0.0417 WL cube by EI, so that is for the distributed load. And by adding those, theta A, theta AW plus theta AR must be equal to slope at A. So when we put the value, so we have minus 0.00769 WL cube by EI. Now we're using this, you can find using the method of superposition, you can find the reaction for statically indeterminate beam, and also you can find deflection and slope at different location. But you have to follow the compatibility condition that and similarly you can solve statically indeterminate problem as well. Okay, let's see this problem 9.77, and we will use method of superposition and that table at NHD. So for that, for the beam loading shown, determine and A, the slope at end A. So we have to find what is the slope at this end A and also what is the deflection at point C. So we have a simply supported beam with a two bonding moment acting at A and B, and the cross section is given, and the modulus of elasticity was also given. Okay, now in order to find theta, now this loading from the appendix T, table from appendix T, this is case 7 and case 4, means I can write this. If I want to find theta A will be equal to theta A, right, due to loading 1, and let me write that is moment at A, plus theta A moment at B, plus theta A due to load at C. Similarly, YC, that we can write YC because of moment at A plus YC due to moment at B plus YC, that is due to load 140 kilonewton. Let me write it as 140 kilonewton due to load 140 kilonewton. So this, when we solve this, this is part A and part B, and the cross section is given. So with that, we can go to appendix C and find what will be the value of I. Now, for appendix T, case 7, so considering the load, this load, that is moment, we considering moment at B. So theta A due to moment at B, so it will be simply equal to ML divided by 6EI. ML divided by 6EI. And M we know that is 80 kilonewton and L is 5. So 80 multiplied by 5, that is in kilonewton, 60 EI. So we have that we can write 66.67 divided by EI, and that will be in terms of 10 to power 3 as well. Okay. Now, deflection at C. So that is the maximum. Now on this equation, we will put x is equal to 2.5 and L is equal to 5. So that will become minus M divided by 6 times E I L x cube minus L square into x, and this will be equal to 80 divided by 6 times E I L is 5, total length of the beam, minus 2.5 cube minus 5 times 2.5 square, and YC due to MB. Due to MB, we will get, if we solve it, putting the value, that is 125 times EI. Okay. Now let's see for this one. Now we're talking about theta c, theta a, sorry, due to moment about b. No, sorry, moment about a. Now this will be, if you look at this equation, now for this it will become theta a and this value, and ml, it will become ml divided by 3 ei, not 6 ei, because if you look at that is giving theta b, but right now the current situation we have, we are considering that ma over here, this portion, same direction, so this slope will be this value, but opposite direction, so the sign will be positive. So m 80, length is 5 divided by 3 ei, so this will give us the value of due to, and this if you calculate, so that will become 133.33 ei. And now deflection will be same, so due to moment a, so deflection will be same, and that will be 125 times ei. Because if you apply movement here or here, so deflection will be same, because it's a same loading condition, same length, but loading is applied on the second hand, so the deflection at the center will be same. Okay, so we don't have to calculate deflection for that. Or if you put again in this equation uh, the values of x and l, you will get the same value. Okay? Because x is same, l is same, and m is same. Now for concentrated load, so let me write theta a, and let me write p. So the maximum deflection is shown over here, this equation. Sorry, maximum slope is shown over here in this equation, that is at the at the end, and that will be equal to minus p l square by 16 ei. Putting the value, p is 140, we know that, l we know is 5, 16 ei. So theta AP will be minus 218.75 ei. And deflection, the maximum deflection will be at C, and because of the load, and we have to calculate at C. So this will be simply putting the value of PL minus PL cube divided by 48 times EI. So putting the value 140 kilonewton multiplied by length of the beam 5 cube, sorry, negative sign over here, divided by 48 EI, and this will be equal to minus 364.583 divided by EI. Okay, now we know the value of EI, we can find from the energy. So the value of E is given, that is 200 gigapascal. I is from energy C for this cross section, so that is 156 10 to power minus 6 meter cube, and EI will be equal to, if you multiply both of them, so EI will be equal to 3 103,100 kilonewton into meter square. Okay, now part A, theta A will be theta A due to moment at A plus theta A due to moment at B and plus theta A due to load B. So when we put the value, we already calculated those values. So that is 67.667 plus 133.33 minus 218.75, and all these values are in kilo. Divide by EI, so we will simply write 13200. So we don't try to write kilo because the above values are already in kilo. So kilo will cancel and we get. Now when we solve it, so that is giving me the value minus 0.601 10 to power minus 3 radians. And the negative sign means that slope, the angle will be in clockwise direction. Okay. Now part B, we already calculated the deflection. So deflection is again yc was equal to yc due to moment about A plus yc due to moment about B and plus yc due to load B. Now moment over here, now this moment will try to take beam upward direction, and this moment is also taking beam upward direction, but this load is pushing the beam in downward direction. So when we calculated the deflection, so we take positive for those deflection that will move upward, and again this is with a kilo, so positive and then negative 364.583 divided by EI, and we already calculated 302.00. EI is common for all of the values, so we put the value, and when we put, so that is minus 303.67 10 to power 3 minus 3 meter, or 367 millimeter in downward direction. So by using table and apply method of superposition, we can find those value of deflection, and as well as we can find the slope acting on the structure. These are the assignment problem related to this method of superposition for statically indeterminate and determinate beam both. Just a suggestion, try to use equation of elastic curve, sum of problem, try to solve it. That is not required for the submission of assignment, but for the practice it will be a good thing to know. And just look at the concept application 9.7 and 9.8, it will further clarify, and also the sample problem 9.9. Okay, now the big question when you talk about for the exam, so you have I will not provide the table, so you have to solve with the elastic curve using the equation of elastic curve. So please practice it, and it's good to know, good to find the deflection through equation of elastic curve. Thank you very much. Next lecture we will solve some problems related to this chapter 9, a different variety of problems, but I will solve through equation of elastic curve. I will not use a table for those problems. Okay. Thank you. Take care. Allah Hafiz.